Let's talk about annuities. There are two different definitions for the annuity. The first is an annuity defined in general, which is simply a fixed amount of money that is either paid or deposited at regular intervals over a set period of time. The second definition is much more specific, and this is an annuity as a financial product. This financial product is a long-term investment that's issued by an insurance company. One of the defining characteristics is the fact that this particular investment offers the investor very low risk, and with that low risk comes very low interest rates. We're going to be focusing on annuities as the general definition. In particular, we're going to be looking at ordinary annuities. Ordinary annuities are those where the payment is made at the end of each month or period. This is the first formula that we're going to be tackling in terms of an ordinary annuity. FV stands for the future value. So the future value is computed by taking the payment and multiplying it by this quantity, 1 plus the interest rate, and that interest rate is per period. So if it was an annual interest rate and you were depositing monthly, it would be the annual interest rate divided by 12. Minus 1, to the nth power, and the nth is the total number of periods. So that might be the total number of months for which you're depositing over the life of that annuity. And then minus 1, and then all divided by that periodic interest rate. This formula is derived from a geometric sequence. So it's summed from this geometric sequence. But let's just apply it to an example. So for this first example, let's say that you've got an ordinary annuity. You're depositing $200 at the end of each month. It earns 12% interest, and we want to know what the value will be after 5 years. So notice these defining qualities of the ordinary annuity. My deposits are a fixed amount. They're also being done at fixed intervals. In this case, it's monthly. I've got my interest rate and a time in years. So as I apply these values to our formula, we see that the interest rate, this is my periodic interest rate, I take the annual rate and divide by the number of periods in a year. So 0.12 divided by 12 is 0.01. The total number of periods is going to be 12 months times 5 years. So we have 60 total periods and those payments of $200. When we put this into the formula, we end up with a future value of $16,333.93 at the end of 5 years. Here's our second example. In the second example, we've got a savings goal of $85,000. How much should you set aside at the end of each month if you're earning 6% annual interest and want to have achieved this goal after 10 years? This would be a really classic example of saving for, say, a down payment on a house. We're going to apply that same future value formula. This time, our future value is the $85,000, and we're solving for the payments. The interest rate, so this is our periodic interest rate, is the annual rate divided by 12, the number of months, and the total number of periods, 10 months over 10 years, is 120 total periods. Putting this into our formula gives us this with payment as the value that we're solving for. On this slide, I take you through the step-by-step calculations. The calculations are tedious, and you want to be really careful as you are computing this. Notice that I've kept as many decimal places as possible, and I've very carefully used order of operations. As I use order of operations, I work inside the parentheses, working with the innermost 1 plus 0.005 grouping first, and then I take the power, and then I continue to work through order of operations to solve for that payment amount of $518.67. I encourage you to go through and do these calculations on your own, making sure that you can match each of my steps here. Now let's talk about the present value of an ordinary annuity. We need a new formula because now we're looking at the initial amount as opposed to the payments or the future value. So we know that the payments is the amount deposited or received at the end of each period. I is the discount or interest rate on a periodic basis, and N is still the number of periods. A good example of a present value would be a loan amount. So what would the initial loan that you would take and then make payments towards this loan? So here's an example. So for this example, we can only afford $500 a month, which is actually a lot for a car loan. The average for an American individual with a monthly car payment is about $500 as well. So let's say that we can afford $500 a month for a car payment. We've got a 36-month car loan that we're looking at that charges 3% per year. How much can you afford in total for that car loan? So we want to find the present value or the loan amount. I'm going to be using this formula here, and notice that I have many of the same variables. So I do have the payment, which is known. I is still the periodic interest rate. So in this case, it's still monthly payments, so 0.03 divided by 12. And my total periods is going to be the 36 months, the length of that loan. I'm plugging the values in here and again going through those step-by-step calculations using order of operations. Again, I encourage you to go through this with your calculator, making sure that you can get the same value that I do for that present value car loan. So the maximum car loan that we can afford with these parameters is $17,193.23. We can also compute the interest, either earned or paid, on an ordinary annuity. Actually turns out to be a pretty simple calculation. We're going to look at the same car loan example that we just calculated, and we know that we can borrow $17,193.23. We've got 500 monthly car payments over a period of 36 months. How much, well, we want to know how much we will be paying in interest. So how much will we pay in interest? So we had the amount borrowed. We also know the total paid. We're paying $500 for 36 months, which totals $18,000. Now we just subtract the amount that we borrowed. So we take that total paid, $18,000, and subtract the $17,193.23. And we come up with that total interest paid of $806.77. There are also annuities due. So we have been focusing on ordinary annuities where the payments are due at the end of each month. Annuities due are when the payment or deposit happens at the beginning of the month. This in essence gives us an additional month for which interest is applied. So we're going to look at a comparison between the two. The ordinary annuities, the column on the left, is what we have been focusing on, where the payments or deposits are made at the end of each month or each payment period. An annuity due is very similar, except the payment or deposit is made at the beginning of the month. So again, in essence, we have one more month for which interest is applied. So you'll notice that what we've got in terms of the payment and the calculation in the square brackets is identical between future value and present value for both types of annuities. The only difference is the value on the end for the annuities due calculations. We've got 1 plus I on the end, which in essence gives us that one additional month of interest applied. So you can easily apply the same concepts that we have worked through for ordinary annuities, applying those concepts to the annuities due with these slightly different formulas. There's lots more to learn about annuities. As you work some practice problems, I encourage you to work through the formulas that I've got presented here, but also take a look online. There are many, many different financial calculators available for annuities that you can find online.